Hello everyone, welcome to Technologies Discussion channel. Okay, today I'd like to continue the discussion on parameters. Okay, so for this video, it's actually the first series discussion on S parameters. This video, I will discuss the S parameters of two-port network. So basically, this is what I mentioned earlier on. This is the first series of discussion. However, if you take a look on the playlist under the description, okay, over there, you will be able to find a series of discussion on Z parameters, Y parameters, ABCD parameters, and also S parameters. So guys, if you're keen to know more about parameters, okay, just take a look on the playlist under the description. Over there, you will be able to find a series of discussion. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are also welcome to ask me your question through the comment. Before I continue, I'd like to urge you guys to help this channel by like this video. Just give me a few seconds by pressing the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly go through the history of S parameters. Okay, so the former first publication that actually described the S parameters, okay, was in a thesis of Vitold Belevitch in 1945. Okay, so basically this is the first start of S parameters. S parameters actually they have lots of name. Okay, so basically S parameters they are called scattering parameters, or sometimes they also known as S metric, and they are actually used to describe the relationship. Okay, focus on the input and output port of an electrical system. Okay, so basically they tell you the response. Okay, based on the input and output ports. Besides S parameters, as I mentioned earlier on, okay, we also use Z, we also use Y parameters, H parameters, T, and also A, B, C, D parameters. So basically, in short, on different scenario, you actually will prefer to use certain type of parameters to analyze the electrical system. Okay, so why we want to use S parameters? Okay, the key reason why we want to use S parameters is because S parameters does not use open or short circuit. For Z and Y, they use open and short circuit. But for S parameters, we don't actually use short and open circuit. Okay, so in order to characterize like a linear electrical network. Okay, so instead of open and short circuit, a matched load, let's say 50 ohm, are typically used. Why? This is because at high frequency, we can't have a perfect short circuit. A wire, which is supposed to be short circuit at low frequency, they are not longer short circuit at high frequency, which means that they are not longer at 0 ohm. There will be some so-called small amount of ohm. However, this can be some effect, okay, on the circuit. So hence also for open circuit, there is no infinite ohm anymore. When the frequency reach at a certain RF or microwave, the open circuit become irrelevant, okay, because there is no infinite ohm anymore. Therefore, at high frequency, we actually will prefer to use S parameters over the many parameters that we have discussed. From the S parameters metric, we can obtain the characteristics of linear network. Okay, firstly, we can get the gain, which I will illustrate later on. The loss, we are also able to get the impedance, the phase group delay, and also the VSWR. Okay, so basically all these parameters I will describe almost at the end of this video. Okay, but this is what we can actually obtain from the S parameters. In the 1960s, okay, so I think this HP should not be new to you. Okay, so this HP actually introduced the first microwave network analyzer. Okay, the vector network analyzer actually measure the amplitude and also the phase of voltage. Okay, using this traveling wave phasor. Okay, so basically this is a so-called a picture of a network analyzer. Okay, so this is a modern network analyzer. This is actually the very first microwave network analyzer. So in short, okay, basically HP introduced this vector network analyzer, okay, to see the frequency versus the amplitude, to see the frequency versus the phase. So basically, this is the first so-called application of S parameters, is to characterize your DUT, for example. Okay, so let's do a very simple question to test your concept. Okay, so again, if I have received enough so-called response through the comment, okay, I will release the answer. But I think this is a very interesting question to test your concept on S parameters. In a two-port network, if S11 is measured at 0.6 at a certain frequency, does this indicate that 60% of the incident power at port 1 is actually reflected back? Okay, so before we discuss what is actually S11, you should know that S11 actually determine something that is reflect. Okay, but maybe when you finish this video, you will have a better idea what is S11. But in short, when we actually measure S parameters, when S11 is measured at 0.6, okay, at a certain frequency, okay, does this indicate that 60% of the incident power will be actually reflected back? Which means that 60% of the power will be reflected back over here. So does this so-called sentence is correct or wrong? Okay, so guys, hope you can participate. Okay, so again, okay, you can always participate through the comment. If I receive enough response, then I will release the answer. Okay, so basically this is a very simple question, okay, to test your concept on S parameters. Let's start our discussion on S parameters. Okay, the scattering S parameters, in fact, they are a mathematical representation widely used in electrical engineering, okay, particularly in the field of RF and also microwave engineering. Okay, so basically, S parameter is actually widely used in a high frequency. High frequency means at a RF frequency or microwave frequency. Okay, so basically, this is used to describe the behavior of electrical network in response to input signal. So basically, when I actually insert the input signal, okay, so basically these S parameters will indicate, okay, how does this input signal will have the effect on the so-called the two different port at the input port and also at the output port. Okay, so basically this we will discuss further. The S parameters actually characterize how RF power is transmitted. Okay, so basically, let's say we insert an incident, okay, we can determine how much can be so-called transport from one port to another port. It also focus on reflect. Okay, so how much is actually reflected. So basically, this will be under the reflected. Absorbed, when you actually pass through a EUT, for example, this is a DUT or EUT, okay, some power will definitely will be lost. So the loss of that form of power, we call this as absorption by a system or absorption by a so-called DUT or EUT, okay, such as a transmission line. So this DUT can be a transmission line, can be antenna or electrical circuit. So basically, in short, there will be definitely some sort of power loss when we actually put a power here and the power actually come out from at the port 2, okay, there will be some form of loss. And when you actually have this form of loss, we call this as a absorption loss. Okay, so basically this is on the S parameters. S parameters change with frequency, which means that S parameters is not valid, okay, from frequency to frequency. Different frequency, you actually have different set of S parameters. Okay, so therefore, frequency must be specified for any S parameters measurement. Okay, so basically when you measure S parameter, you must mention that at what frequency you actually conduct the test and measurement of S parameters. At the test frequency, each element or S parameters is actually represented by a uniqueness complex number. Okay, so basically, later I will mention this basically with an amplitude and also a complex number. Okay, that actually represent like the magnitude. Okay, so this is the amplitude, and we also have the angle. Okay, so over here you actually can see how we actually can describe the S parameters. Okay, so most of the time we actually describe S parameters as a complex number. Okay, the complex number may either be expressed in a rectangular form. Okay, so basically this is a rectangular form, or more commonly in a polar form. Okay, so this is actually a polar form. Okay, so over here you can see that this is actually a set of S parameters. You can see that the S parameters value is actually indicated here. Okay, so basically there's no meaning on these S parameters. I just want to quickly share with you how can we actually describe S parameters. So this form here, we actually describe the S parameters in a polar form. Okay, so basically S11 is actually equals to this. So this is actually equals to S11. S21 is by this, etc. So this is how we describe S parameters in a complex polar form. We can also, okay, describe S parameters in a so-called rectangular form. Okay, so rectangular form means that we have this form here and then plus an imaginary number. real plus imaginary number. Okay, again, let's say S11, this is actually the S11 S parameters value. Okay, so later on we will discuss a little bit more. Okay, so again, if you're keen, okay, you are always welcome to take a look on the playlist, okay, under the description for more information on these S parameters. Okay, the S parameters actually relate the incidence, okay, which is the input and also the reflected wave at the port of a multi-port network. Okay, so this video I will just concentrate on two-port network. Okay, but imagine, okay, so basically S parameters is actually how they actually relate. For example, when we actually incident a wave, okay, so basically we will be able to see the reflected wave, etc. And basically this is how they represent. Okay, basically you can see from here, which is Sij. Okay, so basically this actually represents the relationship between the power entering at port J and the power existing at port I. Okay, so this is where our source is. Okay, this is where we conduct our measurement. So if you want, okay, so later on I will fully so-called explain this as parameters. But again, like to re-emphasize this again, this is where we put our source. This is where we measure. So J is where we put our source. I is where we conduct the measurement, okay, which is shown over here. Okay, so basically S parameters here is actually the output wave at port I, okay, and the incident wave at port J. So when you actually insert a source, okay, basically this will be an incident wave. Okay, for example, for this case is at port J, then you will get some value at the output port, okay, which is at port I, okay, as it illustrated over here. Coming to the advantage of S parameters, okay, let's just do a very quick so-called discussion on the advantages of S parameters. Okay, simplified calculation for high frequency network. Okay, so basically S parameters actually the biggest advantage is basically the easiest, okay, when you actually want to do some form of calculation, especially for high frequency. For low frequency, then I think you don't need S parameters. But for high frequency, you definitely prefer to use S parameter to do some form of calculation. Okay, so they eliminate the need for direct voltage or current measurement. Okay, S parameters, when you actually do this kind of test and measurement, you don't actually measure the voltage, you don't actually measure the current. Okay, when at high frequency, it is always very challenged to measure the voltage value and also the current value. Okay, so basically this is what I mean. Okay, so they are actually impractical at high frequency. So therefore, this voltage and current is actually applicable for low frequency. But once you actually add RF or microwave frequency, then this may be a big challenge. Okay, so S parameters also allow easy representation of multiple port network. Okay, so like I mentioned, this video is only on two-port network, but imagine you can have four-port network, eight-port network, 16-port network, etc. So S parameters, in fact, will be a very easy representation of multi-port network. Okay, let's understand, okay, what is all these S parameters. Okay, so this is the definition of S parameters. Okay, so I guess if I just tell you to memorize this, okay, this become so-called very very dry. Okay, so basically you will not be able to appreciate or understand all this, or maybe once you leave your school, you will so-called forgotten all about this. But now I'm going to share with you a technique how I actually remember all these S parameters. Okay, for example, S11. Okay, if you still remember, I told you that the last one is actually where I put the source, and the first so-called number here is where I actually conduct my measurement. So basically from here you can see that I put my source at port 1, I actually conduct the measurement at port 1. Okay, so this is the S parameters. Again, if you put this so-called S11, okay, on this diagram here, I put my source here at the input of the DUT, and I also conduct my measurement at the port 1 of the DUT, which is the input here. So basically, when you see that I put my source here, so what I'm actually doing is I actually measure what is actually reflected back, right? So basically, I put this incident wave here, and then you know that, okay, they actually will be reflected back, okay, because of mismatch. Okay, so this is where I conduct my measurement. So from here, you can see that this is actually known as input reflection coefficient. I put my source here, and the incident wave will just propagate. So once they hit the DUT, some may be reflected back, some may be continue to propagate. So when we actually use this S11, we actually characterize how much is actually reflected back from the DUT. So therefore, this is what we call the input reflection coefficient. Okay, so this is how we can remember the name. So once you understand the concept, you know that this is actually an input reflection coefficient. Okay, so next will be on S21. So again, this will be where my source is. Remember the two term here. The last one is actually where my source. The first one is actually where I conduct my measurement. So my source is at port number 1. Okay, so this is where my source, my measurement at port number 2. Okay, so this is where I conduct my measurement. So from here, you can see that this is where I insert my incident wave. I actually conduct my experiment at the output. So basically the incident wave actually propagate here and finally reach at the output. So this is what we call the forward transmission coefficient. You can see that how much power, so-called, can be reached at the output. So therefore, in this form here, we call this is a forward transmission coefficient. With these parameters, you actually will be able to know how much power is able to so-called insert over here and how much power will be arriving at the output. So therefore, this number will indicate how much power, when I actually insert at the input, how much power will I actually obtain at the output. So this is for S21. Okay, so next, for S12, so basically this is actually a reverse of S21. So my source now is actually at the output. Okay, so basically I put this is where my source now. Okay, this is where I conduct my measurement, which is at the input here. So from here you can see that I insert my incident wave here and I actually determine how much will be able to propagate and reach at the test and measurement point. Okay, so therefore this form here, is actually called the reverse transmission. Remember, this is called the forward transmission. This is what we call the reverse transmission coefficient. Okay, again, this number will be equals, if let's say the so-called the DUT is symmetric or the filter is symmetric, then when we actually say that they are symmetric, which means that S21 is equals to S12, which I will again emphasize later on. But this is how we can describe this S12, which is known as the reverse transmission coefficient. Let's go through the last one, which is the S22. S22, again, these two number, this is where my source, this is where my measurement. Again, I put where my source, and again, this is where I conduct my measurement. So from here, you can see that this is the incident wave. I actually measure how much will be reflected back, right? So this is my incident wave. I actually conduct where how much the wave actually will be reflected back. So therefore, this form here is actually called as a output reflection coefficient. So hopefully with this, you will be able to understand the S parameters, S11 all the way to S22. So basically, I hope this will be a better idea or explanation for you to understand what is actually S parameters. So before I continue, guys, I'd like to urge you guys again, just spend a few seconds to help by like this video. Again, if you have learned something from this video, please consider to subscribe if you are new to this channel. Thank you so much. So let's quickly understand what is so-called reciprocal. A network is reciprocal. If firstly, they must be passive. Which means that no power actually will be obtained from this DUT or EUT. So they must be passive, and they only contain only reciprocal material that influence the transmission signal. Nowadays there is a lot of different types of so-called material, for example, metal material, etc. So this must be a so-called a reciprocal material, for example, a Roger board, etc., a PCB board, etc. So basically, this is what it means here. For example, antennator, cable, splitter. So splitter for 3-port cannot, but if a general form 1 split to 2 is okay. A combiner and all reciprocal network. So when we actually say that when this is actually reciprocal, this is actually true, which means that SMN equals to SNM. Which means that S12 is equals to S21. This is what I mentioned earlier on, which means that Okay, once we have this reciprocal, okay, we can actually insert over here or at the port 2, it doesn't matter. Because just imagine if this is the incident wave, okay, whatever that I obtain at the output or whatever that I obtain at the so-called at the input port, they will be the same. When I insert my incident wave here, okay, you actually have some form of output and you have some form of reflected. Okay, they will be the same if I insert my incident wave. Same amount of incident wave when I actually insert over here, the same amount will be obtained at the output and also at the output port here. So basically, in short, okay, so therefore, okay, when you actually has a reciprocal so-called DUT, okay, regardless, either the port 1 and port 2 can be the input and output. Okay, so this is to meet so-called the device design to be easier. Okay, so basically you don't need to specify which one is the input, which one is the output. Okay, they can be vice versa. They can be either the port 1 as an input or port 2 as an input or port 1 as an output or port 2 as an output. Okay, so they are the same. So regardless of this, okay, so this is a very important characteristics. Okay, so basically this can be described by using the S parameters. When you actually see this, S12 equals to S21, which means that they are actually so-called reciprocal, which you can use either of the port as an input or output here. So basically, this is what it means. Okay, the network that include non-reciprocal material in the transmission medium. Okay, so like I told you that nowadays we have a lot of non-reciprocal material, metal material, etc., or some newer one, magnetic bias, ferrite component. Okay, so an amplifier is also another example of non-reciprocal network. Okay, so if this is a amplifier, okay, because amplifier, you know that the key purpose is to, if I put it over here, okay, I want to have a huge gain. Okay, so if I put my input here, I can't have this kind of effect. So for amplifier, okay, basically they will state where is the input, where will be the output. So therefore, you can only incident your wave over here, and the signal will be amplified at the output when you actually see over here. So definitely, amplifier is another example of non-reciprocal network. Next will be on lossless network, which means that there is no loss. Okay, everything go in, everything will go out. Okay, so this is the ideal world. Okay, but this is not feasible. Okay, but let's quickly understand what is actually a lossless network. Okay, a lossless network is one that does not dissipate any power. Okay, mathematically, this is what is expressed. Okay, so if you know that this AN is actually all the incident wave, okay, and then BN is actually what we call the reflector wave. When we have this lossless network, okay, whatever that we actually put into the DUT, it will be the same, okay, at the output, which means that whatever, okay, so-called incident wave you actually obtain, they will be equals to the reflector wave. What you put in, okay, you actually will get all at the so-called the, you see over here, these are all the incident wave. Okay, you have this A1 and A2. You also have the reflected wave, which is the B1 and B2. Whatever you put in the incident wave, you actually will obtain the reflected wave because this DUT don't have any loss. So therefore, this is what we know as a lossless network. Okay, so this means that the sum of the incident wave or incident power, okay, at all ports is actually equals to the sum of the outgoing power at all ports. Okay, so basically this is the meaning over here. So these are all the power. Okay, this implies that the S parameters metric is unitary, okay, which means it's equals to 1. Okay, so basically they can be described in this form here. Okay, so basically this is lossless, which is ideal, okay, but not feasible in a practical scenario. Okay, so for the practical scenario, it's actually we call a lossy network, which means that there is some form of loss. Okay, a lossy passive network, okay, is one in which the sum of the incident power at all port, okay, is greater than the sum of the outgoing. Okay, remember this, as I mentioned earlier on, these are all the incident wave. When you actually add all the incident wave, they are actually bigger than the sum of all the reflected wave. So this is what it means. Okay, so for a lossy network, okay, for the practical use case, whatever that you put in cannot be 100% will be coming out from the DUT. Some will be lost, for example, heat loss, etc. So therefore, this is not possible. So therefore, whatever that you actually sum the power at the incident wave, they will be definitely bigger than the reflected wave, the power of the reflected wave. This is what we know as a lossy network. Okay, so next, okay, let's quickly understand the different so-called S parameters properties here. So that you can understand what we actually want to mention. Okay, so basically this is the first one, which is called a complex linear gain. Okay, when you actually see this complex linear gain, okay, let's say we describe this as a polar. Okay, so you actually have the magnitude and also the phase. Okay, so the equation how you calculate, I will describe later on, okay, which is on another video, but this is in general the formula to describe the complex linear gain, which means that they consist the magnitude and also the phase. Okay, so this actually represent the linear ratio of the output reflected power wave to the input incident power wave. Okay, so basically you can see that, okay, at the output, okay, so basically this will be the output, okay, versus the input. Remember, this is what we mentioned earlier on, which is the incident wave. This is actually the reflected wave. So how you obtain the gain, okay, basically will be from this equation here, which is the ratio of the output reflected wave, okay, to the input incident power wave, okay, with all the value expressed as complex quantity. Okay, so basically these two number must be complex. You cannot just insert the magnitude. Okay, so basically this is a full complete way, okay, to describe S parameters using this complex linear gain. Okay, for lossy network, okay, so it is so-called sub-unitary, which means that they are not equals to 1, while for active circuit, okay, so therefore the gain can be more than 1. Okay, when you actually design a power amplifier, okay, the gain, the magnitude of the gain can be more than 1. Okay, so it will equate the voltage gain only when the device has equal input and output impedance. Okay, so basically this is how we actually describe S parameters as a complex linear gain with the magnitude and also the phase. We also can also describe the S parameters under this scalar linear gain, which means that we only obtain just the amplitude, we ignore the phase. Okay, so this represents the gain magnitude, okay, which is the absolute value, okay, defined as the ratio of the output power wave to the input power wave. In short, okay, when you actually describe this as a polar, you only obtain the so-called the magnitude, you ignore the phase. Okay, so basically this is actually equals to the square root of the power gain. Okay, so it is a real value, okay, or scalar quantity, okay, with phasor information on it, which I have just explained earlier on. Okay, so next is on a scalar log gain. Okay, so basically you just need to do 20 log, okay, on this form here. Okay, so this represent the gain magnitude, okay, which is the absolute value, okay, which is the ratio of the output power to the input. Okay, so why we need this? Okay, so this actually measure, okay, they are actually more commonly used as compared to the linear scalar linear gain, which I have discussed earlier on. A positive quantity is in general understood as gain, while a negative quantity is referred as negative gain or attenuation. Okay, so basically in short, when you actually see a positive number, which means that this S parameters is actually a gain. When you see a negative number, which means that they actually attain a power. Okay, so basically all this is all described here. Okay, next on insertion loss. Okay, so for insertion loss is basically when you actually, in case the two measurement port use the same reference impedance, the insertion loss is the reciprocal of the magnitude of the transmission coefficient S21 expressed in decibel. Remember, okay, earlier on I talked about the S parameters. So S21 is actually what happened here is basically I insert at port 1, I measure at port 2. Okay, so basically from here you can see that this will tell me how much will be able to send over. Okay, so basically from here you can see that this is actually 1 over this. So this actually measure how much is actually lost. Okay, if I transmit at port number 1 and I measure at port number 2, this insertion loss actually tell me that how many power is actually lost within the DUT, which is called the insertion loss. So basically, just don't confuse about all these different terms. Okay, insertion loss basically determine how much will be the loss when you actually incident a wave and you actually measure at the output how much will be the loss. So this is what we call a insertion loss. Next, on the input return loss, okay, so this is a formula, okay, to describe the input return loss. Okay, so basically these two are quite similar. This is at the output, okay, which means that at the port 2, this is actually at the port 1. Okay, so I will just quickly describe this. Input return loss is a measure of how efficient, okay, a system or component, okay, for example, we have antenna, we have filter, we have amplifier that is actually match its impedance to the connected transmission line or source. Okay, so basically in short, when you actually look at this input return loss, you can see how well matched it is. Is it 50 to 50 ohm? If you understand what is called impedance matching, from here, if you have 50 ohm matched to the 50 ohm, then you have maximum power transfer. When you actually want to determine this, it will be much easier if you take a look on this input return loss. This input return loss actually will tell you how well that you actually match. Okay, so it quantified the amount of input signal reflected back due to impedance mismatch. Okay, this is what I mentioned earlier on. Okay, if we put some signal at the input, okay, so what happened here is basically this number will tell me how much is actually reflected back. Okay, because due to impedance mismatch, the signal will be reflected back. Okay, so basically this is, in short, this is actually described, okay, in the impedance matching at the input. This, if you want, is actually to describe the impedance mismatch at the output here. Okay, so basically this output return is to quantify the amount of signal power that is reflected back into the output port of a device, okay, such as an amplifier, transmitter, or other RF or optical equipment here. So it is a measure of how well a device or system actually match its load impedance at the output, and it is normally expressed in decibel. Okay, a higher output return loss value indicate better impedance matching and less power being reflected. Okay, so basically as big as possible, we want this number because this actually indicate that it is actually a better impedance matching. Okay, so which means that less power will be being reflected back. Okay, coming to this reflection coefficient. Okay, so this term should not be new if you do this study on S parameters. Okay, so how we describe the reflection coefficient can be at the input, can be also at the output. Okay, when we actually mention about this reflection coefficient, okay, basically for the input reflection coefficient, they will be S11. As for the output reflection coefficient, they will be S22. Okay, the reflection coefficient at the input port or at the output port, they are actually equals to S11 and S22 respectively, which I have just described. The reflection coefficient are complex quantity and they can be graphically represented, okay, on a polar diagram or onto the Smith chart. Okay, so next one will be voltage standing wave ratio. Okay, so basically, most of the time we will use this small s, okay, to describe voltage standing wave ratio here. The voltage standing wave ratio, or you can put VSWR over here, okay, at a port, okay, can be input or output port. They most of the time will be represented by this lowercase of s, which means that this is not capital number, a lowercase of s, okay, which is a similar measurement of a port match to return loss, but is a scalar linear quantity. Okay, earlier on, you can also include the so-called the magnitude and also the phase. But for this case, VSWR is actually just on the magnitude here. So from here, you can actually see how well they actually match. Okay, so the ratio of the standing wave ratio wave, which is the maximum voltage to the standing wave to the minimum voltage here. So basically, this is the definition of VSWR. Okay, so it therefore relate to the magnitude of the voltage reflection coefficient and hence to the magnitude of either S11 for the input port or S22 for the output port. Okay, so I guess again, if you need to know more about this material, okay, you are always welcome to take a look on the playlist. Okay, so you will be able to understand all these parameters. Okay, sorry. So let's come to the last one. Okay, let's do a quick conclusion on the application on the S parameters here. Transmission and reflection coefficient, you can actually do some form of analytics here. So you can assess how much signal is actually transmitted or reflected in circuit and also the component. Okay, for example, you can so-called measure the S parameters in the whole of the circuit or can be by a component. For example, you can measure S parameters on the filter, for example, or on the antenna or an amplifier, etc. Okay, so basically you can measure the transmission and the reflection. You can do some form of analytics. Okay, so basically how much you want to transmit, how much you actually want to reflect based on S11 and S21. Impedance matching. Okay, so basically earlier on I have emphasized on this, how well your impedance matching can be also determined by S parameters. Okay, so this ensure that the device or network, they are actually well matched, okay, to minimize signal loss. Component categorization, which means that you can describe, okay, how well your component is. So basically, in short, they actually describe the behavior. Okay, for example, the antenna, filter, okay, whether is it a passband or or a stop band, low pass, etc. Okay, they can be actually described by S parameters, amplifier, and also many other RF device here. Okay, so the key application on S parameters is actually the vector network analyzer. Okay, so I believe that this equipment is highly used. Okay, if you work in RF environment, you actually will always use this vector network analyzer. Okay, so this actually they measure, for example, the amplitude versus the frequency, or they measure the phase versus the frequency. With the S parameters, okay, you will be able to categorize the components. Okay, so with this, I hope you have a better understanding on S parameters. Okay, so once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.